Hi, Assalamualaikum and Salam Sejahtera. How are you guys? Are you ready? So let's continue our tutorial by discussing question number 5 until number 10. Okay? So let's do it together. Alright, so let's start by question number 5. Okay guys, so let's continue by question number 5A. Alright, so what do we have now? A 6 microcoulomb charge is located 4 meters from a negative 3 microcoulomb charge. Calculate the total electric potential at point P located halfway between both charges. So the keyword here given now is halfway. Alright, so what do we have? Okay, by assuming that this is Q1 and this is Q2. So what do we have? Q1 and Q2 separated by 4 meters. Separated by 4 meters. And then there is a point which is P, okay, located halfway between. Means that it's just at the middle between the first charge and the second charge. So this is point P, where the separation between point P and the first charge now is 2 meters. Also between P and the second charge also equals to 2 meters. Okay. Alright. So now they ask you to calculate the total electric potential. So remember, the symbol of electric potential is V, and V is under scalar. So remember, for any scalar, we don't have any direction, so that we just take the values given. Okay. Alright. So by having negative, we need to use the negative sign in our substitution. Okay. Alright, so first now they ask you to calculate the total electric potential at point P. So the potential exerted on point P now just by Q1 also by Q2. So we just calculate the potential on P by 1 first, and then the potential on P by 2, and then we just total up the values lah. Okay, so for the first one, V on P by the first charge, VP1, V on P by 1 equals to KQ1 over RP1. So K just a constant again, 9 exponent 9. Q1 is the charge of the first charge, which is 6 microcoulomb, 6 exponent negative 6. Alright, and then over RP1. The separation now is 2 meters. Okay, 2 meters. So that you will get VP1 equals to positive 2.7 times 10 to the power of 4 volt. Alright. And then by doing the same thing, we just calculate the potential on P by the second charge, which is VP2. Alright. So VP2 equals to KQ2 over RP2. Again, K just a constant. Q2 is the charge of the second charge here, which is negative 3 microcoulomb. Okay, remember under scalar, we need to use the negative sign here. So negative 3 micro equals to negative 6. Alright, and the RP2, the separation between P and 2 also equals to 4 minus 2 equals to 2. Alright, okay, so that you will get VP2 equals to negative 1.35 exponent 4 volt. Alright, so by getting VP1 and VP2, so we just total up the values. V on P equals to V on P by 1 plus V on P by 2. Alright. So substitute the values calculated just now, which is VP1, also VP2 into this equation, so that you will get VP equals to 1.35 exponent 4 volt. Okay, seems like the values is positive, so that the potential is quite large lah. Okay, but normally by getting negative values of V shows that the values is quite small. Okay, because V is under scalar, we don't have any direction, so the positive and negative sign show you how large the values is actually. Okay. Okay, next question number 5B. Where is it? Okay, this is the question. Alright, so what do we have now? 2 point charges given now, which is Q1 and Q2, are arranged as shown in the diagram below. So what do we have? This is Q1 and this is Q2. Alright, so the electric potential at point P. So in between Q1 and Q2, there is a point which is point P, and then the separation between point P and Q1 is 0.6 meters, while the separation between P and Q2 equals to 0.3 meters. Alright, so by giving you the charge of Q2, which is negative 2.5 exponent negative 6, also the electric potential at point P, which is equals to 1.9 exponent 5 volt, they ask you to calculate the magnitude and sign of the first charge, which is Q1. Okay, alright, how is it? Okay, so again, the potential exerted on P, of course, exerted by Q1, also by Q2, isn't it? So we are talking about VP1, also VP2, V on P by 1, also V on P by 2. So we just calculate VP1 and VP2 first. So VP1 equals to KQ1 over RP1. So again, K just a constant. Q1 is not given here. We just leave it to be Q1 first. And RP1 is the separation between P and Q1, which is 0.6. Okay, so that you will get VP1 equals to 1.5 exponent 10 Q1 volt. Something is missing. The unit here should be volt. Alright, and then by doing the same thing, we just calculate, okay, V exerted on P by Q2. That one is VP2. VP2 equals to KQ2 over RP2. Again, K just a constant. Q2 is given already, which is 2.5 exponent negative 6. Okay, negative. Alright, and then okay, sorry guys, the charge of Q2 given is 2.5 exponent negative 6 coulomb, which is positive. There is no negative sign. That one is typo actually. Alright, so Q2 given is 2.5 exponent negative 6 coulomb. So that we need to calculate V exerted on P, which is by Q2. That one is VP2 equals to KQ2 over RP2. So K just a constant again. Q2 is 2.5 exponent negative 6 and still positive. Okay, and the separation between P and Q2 equals to 0.3. So by using our calculator, you will get V on P by 2 equals to 7.5 exponent 4 volt and still positive. Alright, because Q2 is positive actually. Alright, then by getting V on P by 1, also V on P by 2, so that we just calculate the total V on P equals to V on P by 1 plus V on P by 2. So V on P, the total values given already, which is 1.9 exponent 5. Substitute here. And then VP1 equals to 1.5 exponent 10 Q1. Alright, we just in terms of Q1s. And then VP2 equals to 7.5 exponent 4. Alright, so by using our calculator, then we may calculate Q1, and Q1 getting now equals 7.7 times 10 to the power negative 6 coulombs. Okay, so again, Q2 given here just in positive values. It's not a negative charge. It must be positive charge, so that you will get the answers given or suggested here lah. Alright. Okay, next question number 6. Alright, seems like we are talking about explanation. Seems like the question is under conceptual question, so we need to explain. Using a short sentence enough lah. We don't have to explain details. Alright, so for the question number 681, the question is, how are electric field lines and equipotential lines relative to each other? Okay, so to answer this, we need to know how was the diagram actually. Okay, I'll leave it first. And then 682, describe the amount of work done to move a positive tense charge along an equipotential line. Okay, what to happen to work? Okay, when we are trying to move a particle or charges on, okay, and equipotential lines. So what happened to work actually? And lastly, for question number 6b, they ask you to sketch the equipotential and electric field lines of an isolated charge and a uniform electric field. Okay, I think I need to explain you the answer for question number 6b first, because to answer the question, okay, 6a1 question here, we need to know the diagram. Okay, so this is the diagram for the equipotential lines, okay, for the isolated charge and uniform electric field. Okay, so by giving you a positive, okay, isolated charge, as we know the direction of E just outward, so the orange line here representing our electric field. All right, so that the dotted line here, the dotted blue line here, now representing our equipotential lines or surface. Surface. For this we call it a surface. All right. So please refer to points A, B, and C. All right. So A and B just located on the same surface, isn't it? What does it mean? The radius of A and B, sorry, the distance, or radius still the same. Starting from the center towards A, also starting from the center towards B. They are still the same, isn't it? That is why the potential of A and B, they are equal to each other, because they are located on the same surface at equal R. Okay? But between B and C, see which R is greater. This is RB and this is RC. So which R is greater? RC, isn't it? So that VC smaller than VB, or VB greater than VC. Why? Because B is closer to the positive charge compared to C. Or from the equation of V equals to KQ over R. So V and R, they are inversely proportional. So as we know, RC is greater. So for any greater R, okay, what happened to V? V is smaller lah, because they are inversely proportional, isn't it? So between B and C, VB is greater than VC. Why? Because B is closer to the positive charge compared to C. Alright, so this is for any isolated charge. The surface now just in circle. Alright, and then for by having two different plates, okay, let's say there is a plate which is a positive plate and a negative plate. Oh, the plate is not given here. I think I need to show you. Let's say the plate just be like this. This is the positive plate. Alright, and this is the negative plate. Okay, remember in sketching the diagram, the number of charges in both plates, it must be equal. By having 3 positive charge, okay, for the negative one also it must be 3. Okay, because we are talking about the principle of conservation of charges. Alright, so the number of charges on each plate should be the same. Okay, so by having a parallel plate, the electric field, okay, normally starts from the positive plate towards the negative plate. So this is our E. The orange line here now representing our electric field, which is directed to the right. Okay, and then the equipotential lines now represented by our dotted line here. The dotted blue line here now representing our equipotential line. Again, all the lines now just parallel to the plate, isn't it? So by giving you 3 different points, which is A, B, and C. So A and B still located on the same line, isn't it? Or the distance between A and the plate, the positive plate, also between B and the positive plate, just equal, isn't it? Means that the potential of A and B, they are equal to each other. So that A and B just located on the same surface or line, so we call it as equipotential line, so that VA equals to VB. Compared to C, okay, between VA and VC, which one is greater? Of course, VA greater than VC. Why? Because A closer to the positive plate compared to C. C is quite close to the negative plate, so C is more negative lah, while A is more positive. So potential is under scalar, so that V, positive V, is greater than our negative V, isn't it? So that VA greater than VC here, and VA equals to VB, because A and B just located on the same line, that we call it as our equipotential lines. Okay, all right. So for the first question before, which is number 6A1, they ask you, okay, how are electric field lines and equipotential lines relative to each other? Okay, please refer to the orange line and the dotted line here. At any position, okay, they are perpendicular to each other. See? At any position, they are perpendicular to each other. Or maybe for the parallel plate, still the same. The equipotential lines and E, they are perpendicular to each other. So based on that, we may say that the electric field lines and equipotential lines are perpendicular to each other. Okay. Alright, and therefore number 6A2, describe the amount of work done to move a positive test charge along an equipotential line. Okay, so no work is done when a charge moves from one point on an equipotential surface to another point on the same surface. Why? Because the potential difference is 0. Okay, so as we know the equation of work equals to Q delta V, or work AB equals to Q V AB, isn't it? Alright, so in this case, let's say between A and B here, A and B just located on the same line or surface, so that the potential of A and B equal to each other, where VAB equals to 0. Why? Because VAB still equals to VB minus VA. So when VA and VB equal to each other, VB minus VA giving you 0, isn't it? So by getting 0 here, multiplied by Q, giving you 0 work. That is why. So on the same surface or same line, and there is no work done in moving the charge. Okay, because the potential difference are equal to 0. Okay. Alright, so this is the answer for question number 6. Okay, one more thing, the dashed line represent the equipotential line. Okay, the dash or dotted line here, okay, representing our equipotential lines. Okay, next question number 7. What do we have? A test charge Q0 of 3 microcoulomb is moved from point X to point Y as shown in the figure below. Alright, so there are two different points given, which is point X and point Y. Okay, and then there is a test charge which is moving now from X towards Y. Okay, so how much work is done on the 3 microcoulomb test charge? Alright, so as we know, Q0 now representing our test charge, which is moving from X to Y. But on X and on Y, we have the potential already, which is caused by the isolated charge. The isolated charge now just located 8 meters from X, also 3 meters from Y. So by having an isolated charge here, so that the potential exerted on X also on Y by this isolated charge. And then we just put the test charge here, which is Q0, and then we just move Q0 from X towards Y. So they ask you to find the work done. Alright, so basically we need to calculate first the potential exerted on X also on Y by Q1 by the isolated charge. Okay, so V on X equals to K Q1 over R X1. Okay, before that I need to put X1 here. V on X by Q1, okay, equals to K Q1 over R X1. So K just a constant. Q1 given is 70 microcoulomb, 70 micro. And then Rx1, the separation is 8 meters. So that you will get V on X by Q1 equals to 7.88 exponent 4 volt. And then we just calculate the potential exerted on Y also by Q1 lah. Okay, so V on Y1 equals to K Q1 over RY1. Again, K just a constant. Q1 still the same, 70 microcoulomb. Okay, and the RY1, the separation between Q1 and Y equals to 3 meters. Okay, 3. So that you will get VY1 equals to 2.10 times 10 to the power of 5 volt. Okay, so now from the equation of work done from X to Y. Work done from X to Y equals to the test charge, which is moving now from X to Y, is Q naught, multiplied by V final minus V initial. V final is V on Y by 1 before, and then minus by V initial, which is V on X by 1. Okay, so this is V. Alright. So VY1 calculated before is 2.1 exponent 5, substitute here. And then Vx1 equals to 7.88 exponent 4, substitute here. And then you will get the answers, which is 0.39 joule. Okay. Alright, so remember, the potential exerted on X and Y just caused by the isolated charge. And then we just put the test charge on X, and then we just move it from X towards Y. Then the work is done here. Alright, so this is the way lah. We just calculate the potential on X and on Y by Q1. By getting the potential, we may calculate the potential difference. Okay, so that this is our Q naught, which is moving from X to Y, so that you will get the work done in moving that test charge, okay, which is from X to Y. Okay guys, next question number 8. Okay, what do we have now? A test charge, which is 2.5 exponent negative 7 coulomb. The magnitude of the test charge now is 2.5 exponent negative 7 coulomb. Is initially located 7 meters from a fixed 8 exponent negative 6 coulomb point charge. Okay, there are two different charges. The first one is our test charge, and the second one is our isolated charge. How do you know? Please check the magnitude. See, the magnitude is smaller for our test charge. Okay, so this is the test charge, and this is our isolated charge. So they are separated by 7 meters initially. So this is our test charge, and this is our isolated charge. They are separated by 7 meters. Alright, calculate the minimum amount of work required to move the test charge by 2 meters closer to 8 exponent negative 6 coulomb. Okay, so what do we have now? Initially, the separation between the test charge and the isolated charge is 7 meters, and then we need to move the test charge 2 meters closer. Means that initially the separation is 7, and now we just move the test charge by 2 meters. Okay, so that the separation between the final position here and the isolated charge is 7 minus 2, which is equals to 5. Okay, alright, so they ask you to find the minimum amount of work. Alright, so as we know, work equals to Q naught delta V, or work from initial to final equals to the test charge Q naught multiplied by V final minus V initial. Okay, so that we need to calculate the potential on these 2 points, which is initial point and the final point. Okay, so V initial equals to KQ over R initial. So K just a constant. Q is the isolated charge, which is 8 exponent negative 6. And the separation between the isolated charge and the initial point before is 7 meters. Okay, so that you will get V initial equals to 1.03 exponent 4 volt. And then by moving the test charge 2 meters closer, okay, to the isolated charge, okay, what happened now? V final, so this is the final position, okay? V final equals to KQ over R final. Again, K just a constant. Q is the charge of our isolated charge, which is 8 exponent negative 6. And R final is the new separation between the final position and the isolated charge, which is 7 minus 2, giving you 5 meters. Okay, 5 meters. So that V final getting out is 1.44 exponent 4 volt. Okay, by getting V initial and V final, we just substitute into the equation of work. Again, work from initial to finals equals to test charge Q naught multiplied by V final minus V initial. So V final substitute here, also V initial substitute here, and then Q naught given is, where is it? The test charge is 2.5 exponent negative 7. Okay, substitute, and then you will get the work done equals to 1.03 exponent negative 3 joules. Okay, so this is the way. Don't be confused. Okay, normally the potential exerted on each point now just caused by the isolated charge. Okay, and then we just move the test charge. So the test charge doesn't contribute any values of potential on these 2 points. Okay, so the potential on initial and final point just caused by the isolated charge only. So that by having potential here, then we just move a test charge from initial to final, then the work needed there, okay, caused by the potential on both points. Okay, so what do we have now for question number 9? 3 charged particles are located at the vertex of an equilateral triangle as shown in the figure. Okay, so by giving you Q1, Q2 and Q3, where Q1 is a positive charge, also Q2, but Q3 is a negative charge, where the magnitude is 2 micro, 7 micro and 4 micro. Okay, they ask you to calculate the potential energy of the configuration. Okay, so based on this, how to calculate the total potential energy? Total potential energy now depends to the number of couple. Okay, how many couple do we have? Okay, for this, the number of couple that we have is 1 2, 1 3, also 2 3. Only 3 couples here. 3 2 still the same with 2 3. Same couple, isn't it? So the number of couple here just 3 only, which is 1 2, 1 3 and 2 3. So the total of potential energy equals to U12 plus U13 plus U23. Okay, so we just calculate U12, U13 and U23 separately. U12, U13 and U23. So U12 equals to KQ1 Q2 over R12. U13 equals to KQ1 Q3 over R13, and U23 equals to KQ2 Q3 over R23. Alright, so we just substitute all the values, which is K, Q1, Q2, also R12. R12, where is it here? Equals to 0.5. How do we know? Equilateral triangle means that the length for each side is still the same, which is 0.5. Okay, so that you will get U12, and then again K, Q1 and Q3, also R13. R13 is still the same, which is 0.5. But remember, U is under scalar, so that Q3 given is negative, so don't forget to put negative sign here, so that you will get the potential energy just in negative values. Alright, And then U23 equals to K, Q2, Q3, okay, substitute all the values. Also R23, still the same, 0.5. And again, Q3 also negative here, alright, so that you will get U23 also in negative values. And so that U total equals to U12 plus U13 plus U23, okay, giving you negative 0.96 joule. So the energy now is negative. Okay guys, so last question, which is number 10. Okay, what do we have now? A beam of electron is directed to a region between two oppositely charged parallel plates as shown in the diagram. Okay, so this is the electron which is moving to the right, just pass through the parallel plate here, where the upper side now representing our positive plate and the bottom one representing our negative plate. Okay, so when the electron just pass through these plates, what happened? Okay, determine the electric force exerted on the electrons in the region between the horizontal plates when they are connected to a 9-volt potential difference. So by applying 9-volt potential difference between these two plates, they ask you to find the electric force exerted on the electron. Okay, first. And second, calculate the magnitude and direction of velocity of the electrons when they exit the second set of plates and sketch the path travel of the electrons. Okay, the electron just pass through the plate. They ask you to find the speed when the electron just reach, okay, the another ends of plate here. Alright, so what is the magnitude and direction of velocity when it just reach, okay, end of the plate here? Alright, and then the info given here, just the charge of electron, which is 1.6 exponent negative 19 coulomb. Okay, this is the index number actually, negative to the power of negative 19. And the mass of electron also given as 9.11 times 10 to the power of negative 31 kilogram. Okay, so they ask you to find the speed. Okay, so what happened now? Based on that, seems like by having potential difference, so there must be an electric field. So the electric field just directed downwards. Why? Because normally the electric field start from the positive plate towards the negative plate. So this is our E. Okay, so the electron just move parallel to the plate, but seems like this is a negative charge. The negative charge will be attracted by the positive plate, isn't it? So what happened now? It just move to the right, at the same time moving upwards there, and because attracted by the positive plate. So we are talking about parabolic motion here. All right. Okay, so based on this, they ask you to find the speed, okay, when the electron just exit the second set of plates here. So they ask you to find V, where V now still equals to the combination of Vx and Vy. Okay, so they ask you to find V, also the direction which is theta. Oh, theta is missing here. Also direction which is theta. Okay, first they ask you to find the electric force. So where is the force actually? Okay, when the electron just enter the region, yeah, with E here, and seems like the force exerted on it, which is Fe, the electric force. And according to Mr. Coulomb, the negative particle will be attracted by the positive plate. So this is Fe. So remember, from the equation of F equals to Ma, so that Fe equals to Ma, so that F directly proportional to A. So in this case, the electric force just lay on the Y component, means that the acceleration also lay on the Y component. So that the speed on Y component varies with time. Why? Because it's just affected by the acceleration. But on X component, there is no acceleration, so that V on X equals to Ux. So where is Ux? So this is Ux. Ux equal to the speed given before. because the speed is really on x component initially, isn't it? Initially the speed is really on x component, so that v given here equals to ux, where ux still equals to vx. It doesn't affected by any acceleration. But on y component we need to calculate vy. Why? Because on y component we got acceleration here, so that the speed change already, and because initially the speed is really on x component, so uy equals to 0. There is no speed on y component initially. Okay, but finally we have vy here, so that we need to calculate vy later, because we need to calculate v, which is the resultant of vy and vx. Okay, so first they ask you to calculate the electric force, so based on F equals to QE. Okay, F equal to QE, so Q is the charge and then E is the electric field. So between two parallel plates, the electric field is V over D. So V is the potential between plates and D is the separation between plates. Alright, so the separation given is 0.020 meters, and then the potential difference given is 9 volt. Substitute here, and then Q is the charge. The charge now is the charge of electrons, isn't it? So the charge of electron is 1.6 exponent negative 19. So substitute into this equation, so that you will get the electric force exerted on the electron is equal to 7.2 exponent negative 17 Newton. So this is the electric force exerted on the electron, causing it moving upward there. Alright, okay, now they ask you to find the speed and also its direction. Okay, when the electron just exit the second set of plates here. Alright, so as we know, V equals to, we need to calculate V. So V equals to square root of Vx squared plus Vy squared. Okay, so Vx equals to Ux. Why? Because on x component there is no accelerations in it. So Vx still remain constant, equals to initial speed, which is on x component Ux, where Ux is given already, which is equal to the speed given here. Okay, that one is Ux. Alright, so that now we need to calculate Vy. So how to calculate Vy? Using Voigt equation. Okay, where is Voigt equation? Vy equals to Uy plus At. But in this, for this equation, A and T is not given, isn't it? So that we need to calculate A and T first. How to calculate A? Okay, we just calculate T first lah. How to calculate T? Using Sx equals to Uxt. So this is Sx. Okay, the displacement on x component equals to 0.12 meters, equals to the length of the plate. So Sx equals to L, which is Uxt. So Ux equal to the initial speed given before is really on the x component. So this is our Ux, and 1.2 exponent 7. And then the displacement on x equals to the length of the plate, which is 0.12. Alright. And then you will get T. T getting out is 1.0 times 10 to the power of negative 8 second. Okay. And then we need to calculate the acceleration. How to calculate the acceleration? From the equation of F equals to ma. So what F is that? The electric force calculated before, which is 7.2 exponent negative 17. That one is F. Mass is mass of the electron given already. Okay, 9.11 exponent negative 31. So that you will get the acceleration. Acceleration getting out is 7.9 exponent 13 meter per second squared. So by getting T and A, and then we just substitute into the equation of what on y component, Vy equal to Uy plus At. So A and T calculated just now, substitute into this equation. Uy equals 0. Why? Because here initially the speed is really on x component, so automatically Uy equals to 0. Okay, so Uy equal to 0, so that you will get Vy. Vy getting out is 7.9 exponent 5 meter per second. So by getting Vy, and then we just substitute into the equation of resultant of the speed, which is v equal to square root of vx squared plus vy squared. So this is vy, substitute here. Vx equals to ux, which is the initial speed given before. This one, this is ux. Okay, substitute here, and then you will get the speed. The speed getting out is 1.2 exponent 7 meter per second. Alright, and then how do we calculate the angle or direction? Using tangent theta equals to Vy over Vx, or theta equals to arctangent Vy over Vx. Substitute Vy and Vx calculated before. Alright, and then you will get the theta equals to 3.77 degrees. Where is it? Above the positive x-axis. How do we know? We just take out the axis. Alright, Vx is positive, Vy also positive, so that the resultant just here lah. So that this is the angle. So the angle is above the positive x-axis. This is positive x and this is negative x. Seems like the resultant just located in the first quadrant, and the angle should be above the positive x-axis. Alright, and then they ask you about the to sketch, okay, the path travel of the electron. Okay, so this is the path through by the electron lah. It's just in parabolic path. Okay, so this is the path through by the electron, which is in parabolic path, okay, towards the positive charge plate, because according to the Coulomb's law before, different charges will attract each other. So the negative electron here will be attracted by the positive plate. So this is the pattern or the path through by the electron. Okay, I think that's all for question number 10. Okay guys, so that's all for chapter 1 tutorial. So I think we have completed, but I think it's not enough, okay, for you. So to try to understand the concept by answering any past year's question, so that you will know the pattern of the question asking, right, in the exam later. Alright, so let's continue by tutorial 2 later. See you again. Thank you. Assalamualaikum.